All right, well, we seem to have a sort of fair few people on board now, so I will just start kicking off with some of the introductions. So hello, everyone. Thank you so much for joining us again for another of our Tea with the Experts webinars. These started when we first went into COVID and lockdown, and it was just really nice to have cup of tea with someone and a bit of a chat. And so that's where these came from. And they've been a really wonderful way for us to share the work that we're doing and the work these incredible researchers are doing with all of you. So I hope you enjoy it today. Just a reminder, we are recording the webinar. So if anybody wants to watch it later, I'll send out the link later today. So if you have to leave for any reason, I will be sending that link through. If you have any questions throughout the webinar, there's a little Q&A box at the very bottom of the screen. If you just type your questions in there, we'll compile them all at the end and go through those. We are so fortunate today to have Dr. Carmine Gentile and Dr. Avedis Ekmejian join Chris and myself to share the research they're currently working on. Dr. Carmine Gentile leads a globally recognised cardiovascular tissue engineering and bioprinting program at the University of Technology at Sydney, collaborating with leading cardiac clinicians. He leads an interdisciplinary lab with 14 team members and is a strong advocate for women in STEM, with 64% of his group being women. It's one of the things we love so much here at Heart Research Australia, because we're quite passionate about funding women and really passionate about women in science, research and cardiology. Carmine was the first to show that tissues containing mini blood vessels can be created as vascular spheroids, which behave like real blood vessels. His international high standing and leadership is supported by numerous invited national and international presentations and editorial roles in high impact journals. Dr. Avedis Ekmejian is a cardiologist with specialist training in minimally invasive cardiac procedures. He's a PhD researcher through Heart Research Australia and the University of Sydney, based at Royal North Shore Hospital. His main research passion focuses on identifying opportunities to improve the detection of ischemia, which is reduced blood supply to the heart, using invasive and non-invasive tests. We are so incredibly grateful to have both of you here today, because I know how incredibly busy you are, so it means a lot to us to have you share your research with us. Most of you will know Chris Russell, who is our host today for our Tea with the Experts webinar. He is one of our wonderful ambassadors, and he runs his own podcast called Ag Reminders. He generously volunteers his time to host these webinars for us, and we are so incredibly grateful for him for his support. And I'm sure that by the end of this webinar, you will be too, because he really makes everything so simple and easy to understand. So he's got a real knack for doing that, and something we're very grateful for. So thank you so much to all of you for coming along, and for our wonderful researchers and Chris for taking their time to chat with us. And without wasting any more time, I will pass you over to Chris, and I'll come back at the end to go through everybody's questions. So feel free to pop them in the box at the end.
Yes, well, Jenny, I mean, listening to those CVs, it makes your mind spin, you know.
Absolutely.
I don't think you guys, I don't think your mothers could have written better CVs for you. So we're finding out about this. But one of the issues, I think, for all of us is understanding exactly what you're doing and where we're going. So that's what we're going to try and do today. And perhaps if I could start off with you, Carmine. We talk about heart attacks and we talk about heart failure. What's the difference?
Thanks, Chris. And let me thank Heart Research Australia and Jenny for the kind invite to talk today to you guys. And thanks for the opportunity to showcase some of the research that we do. And I think it's, as you pointed out, Chris, it's really important that we understand basically what we're trying to achieve here and what are the basic questions beyond all of this. So during a heart attack that happens every 10 minutes on average in Australia, and it's fairly consistent throughout the globe. The blood vessels that bring blood, including oxygen and nutrients, to different areas in the heart, are basically going through this blockage that basically prevent cells from living in a normal way. Therefore, if the patient is able in enough time to recognize the symptoms of a heart attack, that many cases are confused with general like dizziness, headache, and so on. In that case, the patient is able to run to the hospital. The cardiologist is able to reopen the blocked blood vessel and restore blood flow, therefore bringing oxygen and nutrients to that area. Now, unfortunately, 1 out of 4 of these patients are not lucky enough, and therefore the damage caused by the extensive lack of oxygen and nutrients to certain area of the heart is basically leading to the fact that the heart is not able to recover well. At the same time, the damaged part that suffer from this extensive prolonged heart attack is going into a failing state, which is actually characterizing a failing heart. Therefore, this happens 1 out of 4 heart attack patients. And if you make your calculation every 40 minutes, there is going to be on average a new heart failure patient in Australia. And if you do more of your calculation, we are talking about 13,000 new heart failure patients on average in Australia. If we think about what is the state of the art in treating these patients, besides obviously being able to place in a stent in case the patient is able to recognize the symptoms.
If I just
really
before you go,
Chris froze.
Oh, I can try some for me too. Hopefully he comes back soon.
But just summarizing, only few heart transplants are available in Australia. Oh.
Sorry, Chris, you just froze for a bit.
Can you hear me now?
I can,
Yes.
yep.
So, sorry, I just wanted to summarize the key issue here is that when you have a heart attack and the blood stops flowing to a bit of the heart, some of those cells are killed, and therefore that bit of the heart won't be as good as pumping the blood from that point on, and that's heart failure. Is that right?
Correct. So
1 in 4 people who have a heart attack will get some form of heart failure, and that's a completely different treatment to the heart attack. Am I right?
Correct. So the real
and so what do you do what do you do then to treat the heart failure?
I don't do anything. So people like Avedis are able to place a stent if the patient is one of those lucky enough to get the treatment in place. Nevertheless, some cases there is no real treatment. So if the damage is so extensive, the best hope for the patient is that they might receive a heart transplant. Now, based on my calculations that I was going through before, on average, there is around 100 hearts transplanted in Australia every year, whereas you have a demand of around 13,000 new heart failure patients. So there is a huge gap. And so there are different ways. Can we just treat these patients, or can we do something else, including preventing the toxic effects of a heart attack leading into heart failure? And that's where the latest research in my team is trying to understand how can we better understand how the heart attack is leading to heart failure, and how can we prevent this toxic effect from the molecular and cellular level.
So do all of the cells beyond the blockage get killed, or only?
Well, that was a very important question. And so what we tried to understand was, I think I got your question, Chris. So you're asking me, are all the cells in the muscle wall dying, or there are some specific ones that die versus others?
Yes, correct.
Good. So that was a very important question, because from that we can understand on how to better treat or prevent the toxic effects. So in our study, what we have done, first of all, we had to understand on how to recreate what happens in a patient's heart following a heart attack. So we developed what we called a heart attack in a petri dish. Basically, we developed a way to study, including cells from the patients as well, the conditions that are typical of a heart attack. And as I mentioned to you, during a heart attack, the blockage of the blood prevents the delivery of oxygen and nutrients. And so we basically exposed the bioengineered mini hearts that we create in our lab to these conditions where we exposed to different concentrations of oxygen. So we basically depleted oxygen, and we look at the response of these cells in a petri dish. Our results show that basically the cells that are responsible for the contractile function, basically for the beating activity typical of the heart muscle, are all dying. So in absence of oxygen, all of these cells are basically lost. There is not much you can do about it. Nevertheless, we observe that some of the other cells which are present within the muscle tissue are actually surviving. Where in some relationship, around 30–40% of them, they actually survive. So we are trying to understand, is there anything else we can do better in understanding on developing new molecular targets or new molecules, new drugs, to basically help the cells that are surviving to support the muscle cells that are actually dying? Or is there any other way we could work around it to basically prevent these toxic effects on that are leading to heart failure following a heart attack?
So how is this heart attack you're creating in the petri dish? You think it's a reliable indication of what the cell's actually doing in the heart?
So that's a really critical question as well, because as bioengineers, we claim we are able to replicate natural conditions in a petri dish, which is an artificial tool. So for instance, what you see behind me is not my hair growing in a weird way, but it's actually what you would see under a microscope of a mini heart. So I don't know if you can appreciate it contracting, moving now and then. Sorry, and you see it's shaped as a ball. And in fact, we call them mini hearts or cardiac spheroid, just because of the shape, which is spheroidal. Now, if you're able to highlight the different smaller components, each individual dot within this moving entity is actually a cell. So this is actually representative of a healthy mini heart that is contracted. And using microscopy techniques, we were able to understand, besides the fact that these cells stop contracting when we induce a heart attack in a petri dish, we were able also to understand which cells were dying, as I was mentioning to you. But we had to basically validate our findings in some way. So we couldn't basically go and look into the heart of the patient. So what we've done, we had access to human heart biopsies here in Australia and with collaborators at Harvard Medical School, where we were able to understand how representatives our infarcted mini hearts were of the other of the human infarcted tissues that are isolated from the biopsies of the patients. So this validation component was performed as part of our study as well.
So once you've had a look at this and you've understood a little bit more about what makes some cells still able to contract and some cells not able to contract, I remember when we spoke last time, I think you said to me, we're a white mouse now, there's no problem with heart failure anymore. We're all white mice are now good, all we got to do is transfer it. Do you think this might lead to some sort of possibility for immunization effectively against heart failure by putting something in the heart to stop these other cells from dying?
First of all, let me just clarify. We have no colors in our research, white, black, and so I know what you're referring to. But yes, we were successful in another side of the project, which is basically trying to understand on how to create heart tissues in the lab and hopefully prevent this heart failure by transplanting these cells in an infarcted heart. So we actually finished this study in small animals, in mice, and we are very happy about the results that are under what is called peer reviewing phase. So we are resubmitting we are trying to address some of the comments that the reviewers addressed. But in our hands, we received very positive results. And obviously, in order to translate these results to to the patient, we are working on more clinically relevant testing in a later phase. But ultimately, there are lots of steps that are still required for us to basically be able to to make sure that our technology is available to the patient. Nevertheless, the heart attack in a petri dish is a very interesting useful tool because can be utilized by basically anyone worldwide. So basically by sharing the protocols that we have developed here at UTS and Sydney, also thanks to the support of Heart Research Australia, we've been able to create a platform that can be utilized in different laboratories and including companies that are trying to evaluate not only on how to prevent, on how to develop new drugs that might lead to, that might treat heart failure, but also to prevent toxic effects. For instance, in the same study, we also evaluated, for instance, a drug that is used to treat leukemia and lymphoma in pediatric patients that we know is very toxic for the hearts of these kids, which leads to heart failure even 17 years following the treatment. So these kids, they never had a heart attack. Nevertheless, their heart is being exposed to toxic molecules, and therefore there is a toxic effect that is preventing the heart from pumping and working properly. But this is a very common problem with chemotherapy, and we were able to identify this toxic effect within 1 day. So there is hope that our technology might help in understanding not only what are the effects following a heart attack leading to heart failure, but basically multiple mechanisms that might be able to prevent the establishment of heart failure in patients.
So, I mean, I absolutely not enough of it these days, which we don't know what we're going to get out of it in the future. It's amazing the intrigue. But you had to look at 5 to 10 years down the track. What do you think you might be hoping that patients will be able to look forward to, heart failure patients, in 5 or 10 years' time?
I think that, you know, everybody's looking at different strategies. By having the opportunity to talking to the clinicians as well, we know that there is much more advancement in the treatment from the hospital point of view, that even the way heart failure is developing is changing because more and more patients are able to run to the hospital. They get the proper treatment. Nevertheless, the heart is very sensible to this lack of oxygen and nutrients, that there are new ways that the heart is failing compared to the past. So we hope that our results might be translatable and useful to the clinic as soon as possible. As I said, from the point of view of the long-term goal of transplanting these healthy tissues in a patient, we are talking about going through all the preclinical and clinical phases in 5-10 years time. Nevertheless, studies including the heart attack in a petri dish is not so far along, because we are able to use this technology nowadays, and it really depends on the scientific question asked within the laboratory that is enabling the technology to help with different questions.
Now, Avedis, if I could come to you now and talk to you a little bit about the heart attack part of this equation. When you have a partial or a narrowing, you know, not a complete heart attack, does that still kill cells? Does it just kind of slow them down, you know, a little bit in the future? Is it an all or nothing thing? How does a partial narrowing affect the heart?
Yeah, that's an excellent question. And just to start off with, again, also just want to echo my thanks to Heart Research Australia for supporting my research. So to answer your question, partial narrowings can cause a number of clinical syndromes, the most common of which is angina, where when people exert themselves, the demand on the heart is not met by the supply of blood to the heart. So as a result of that narrowing, there's insufficient blood going to the heart. So that tends to cause chest pain without damage to the actual myocytes or the actual cardiac cells. So a heart attack is when there is a complete blockage of the artery that does cause the damage to the myocytes. So to answer your question, yes, it is an all or nothing event in a sense, but it's a bit more complex than that, because obviously narrowings can progress, and so yeah, it's certainly it's a dynamic situation, but yeah, partial blockages tend to not cause damage to the heart cells themselves.
So just leaving the health budget to one side for a second, why don't doctors just analyse everybody at the age of 60 and just whack a whole bunch of stents in just in case they narrow up one day?
That's an
I know it'd be
excellent
expensive, but leaving the cost out of to one side.
That's right. Yeah. Look, the main reason is because these procedures don't come without risk, and that's why we need to have valid reasons in order to do everything that we do. So the evidence points to the fact that people only benefit from these sort of stenting procedures if there is a certain amount of limitation of blood flow, which we can detect by putting very specialized pressure censored wires through the narrowing to determine if there's a limitation of blood flow. So everything we do is a risk benefit assessment, and the risk certainly the evidence demonstrates clearly that the risk outweighs the benefit in the majority of people, and that we need to do specialized tests to validate putting in stents.
So as I understand it, there are a couple of different bits of wire you can shove up there to have a look at, and they don't always agree. How does the doctor still then make his decision if he's going, yeah, well, on one hand, but maybe on the other hand,
Yeah.
How do they work that out?
So that's exactly right. So that's what my research is focusing on. So there are two main modalities that are used. So one of these little wire technologies picks up what we call resting ischemia, where in a normal state, when the patient's lying on the table having this procedure done, the wire determines if there's a limitation of blood flow. Another wire technology requires that we stimulate the heart a little bit with a medication and determine under a stress sort of situation, is there a limitation of blood flow? So those are the two technologies. And what we've found and what's been established in the literature is that these two modalities don't always agree. From a anecdotal and practical point of view, if one of the modalities shows that there's a limitation of blood flow, the clinician will usually listen to that modality and put a stent in, but that is an evidence-free zone. So we actually don't know if that's the right thing to do or not. But it's just I guess a educated guess, more or less, that if one modality shows that there's a limitation of blood flow, then that's what we should do. We should put in a stent.
Okay, guessing when they're fiddling around in your heart doesn't sound good to me. So tell me how your research is going to help that decision-making process.
Yeah. So the first part is to understand the why. Why does one test tell us it's positive and one test tell us it's negative? So what I'm trying to do to answer that is do a couple of things. One is I have a specialized wire, which basically determines if the heart's response to this medication that's given to stimulate the heart is adequate. So you can if this medication doesn't stimulate the heart, that means that we're going to under-detect a limitation of blood flow using that particular technology. Okay, so that's one thing that I'm looking at to try to see, do certain people have less responsiveness to this medication? Okay, so that's one thing. Another element of my research is to actually look at the nature of the plaque itself, to look at the consistency of the plaque. Does calcium in the vessel wall or the plaque limit the utility of one modality versus the other? Does soft plaque versus fatty plaque change how one modality is? Does that impact the accuracy of one modality or the other? So those are the two main things that I'm doing to try to look at the variables that might contribute to what we refer to as discordance between these modalities.
One of the things I'm always nervous about, my son's an intensive care nurse, and he talks about all these bureaucrats making decisions about whether you use in or treat people or not. Needs to be money. How can we be sure that this is not going to be just used by the bureaucrats as a means of saving money?
Yeah, look, it's a very good question. Yeah, look, I think at the end of the day, our clinical decisions are always supported by the bureaucrats. At least in the cath lab setting, we where these procedures are done. I don't think there's ever been a bit of equipment or a test that we needed to do that we've had to rationalize and say, no, unfortunately, this is going to cost too much, or we're going to we're going to have ramifications of this. But I will say that Medicare now is only rebating stents if they meet certain criteria. So one of which includes these pressure wire tests. So it's very important that that we actually, if that is the standard by which we're performing these procedures, we've got to make sure that the technology is accurate. So
do you think the health outcomes for people who have narrowing as against a heart attack is going to be better once with that information? Do you think most docs will just whack a stent in anyway?
Look, that's what I'm trying to refine, because as I've said, the evidence shows that stents are not benign. Stenting is not a benign procedure. So we really need to, and can do more harm than good. So we really need to try to refine the subgroup of people that actually do need stents if there's a limitation of blood flow. So I think there are practical implications. And what I hope is that we actually reduce the number of stents that we need to put in as a result of doing this research.
So do you think the decision-making in your eventual outcome will become more foolproof in terms of, I don't mean that people are fools, but I mean more mistake-proof, I should have said.
Well, yeah, that's right. Look, I think that that we would be able to say in certain subgroups, well, this is the pressure wire modality that we should be using rather than the other pressure wire modality. That's what we should be listening to. So that's what the focus of this research is. In a calcified vessel, should we use this FFR technology or the other wire, which is called IFR? So that's a sort of example where I think we're just trying to refine how we approach putting in stents, basically.
So, Avedis, of all the thousands of projects potentially sitting in front of you when you were deciding where to focus your brilliant sort of mind in this area, why did you choose this as being the one you really want to focus on?
Yeah, excellent question. One is that it's pretty much a clinical conundrum that I face almost every day. So most research is born out of a clinical need, and I do these procedures, every single day, and I can tell you that every other day we have this sort of clinical conundrum. So what that exposes is that it's a fairly it's a common problem in the community, and something that has implications in cost saving for the government, and also has implications in reducing harm for patients by doing less unnecessary procedures. So those are the main reasons.
So, I mean, I've always been, well, obviously, I've been an ambassador for a long time for Heart Research Australia, because a lot of the stuff that they have focused on has been absolutely transformational. And you actually don't see, I mean, in my world of agriculture, you don't see a lot of transformational research. You see a lot of research which is interesting and it's good and helpful and productive, but not transformational. And yet you look at salami, the stenting itself, it's a solve a heart attack. You look at ATAMI, which saved me. It's the only reason I'm talking to you today is because there were 3 ambulances fitted out by Heart Research Australia with this ATAMI communication system where the ambos could talk to the hospital and cut out a couple of hours of time. That's transformational in people. It's transformational in my life. I met grandchildren I never would have met if it hadn't been for that. Do you think this is potentially as transformational as that?
Look, I'd love for it to be. Those are the sort of big footsteps that I have to follow. So I think the first question with every research project is the why, and that's what I'm trying to get at here. And then the next step would be the how. How do we apply what we've learned here? If I can find, for example, that we shouldn't be doing one modality in a calcified vessel, for example, then we would know in the future how to target our assessments a little bit better. So I think I think it's going to be a long process. And I think this is the first part of it, is to find out the why things are the way they are, why we're getting a discordance between the different modalities. And then my next research question, which will probably be in a year or two, is how can that be applied? So long way ahead of me to start saving lives, but from this research project, but I'm ambitious, so I think it'll hopefully get done.
Wonderful. Can I ask you the same question, Carmine? Do you think what you're doing in understanding what's molecularly happening and in terms of killing cells and why some survive and some don't survive, is that potentially transformational in the way we handle heart attacks or heart failure more in the future?
Thanks, Chris. Obviously, this is the holy grail for us. So this is the motivation that is driving us on our daily research. Unfortunately, the nature of research is that you face lots of failures until you actually receive an answer. But ultimately, we are trying our best by working not only within our small niche community, but by understanding better through the communication with the clinicians, industry partners, and so on, regulatory bodies as well. Like some of our recent publication was highlighted by the TGA as well. And we're trying to understand on how to make it transformative or translational, if you want, as quick as possible for the patient, so that our findings are not sitting in a laboratory desk, but are actually able to help with preventing and treating the patients here in Australia and everywhere in the world.
So with this sort of research, is this something that like drugs takes years and years and years before it's approved for use, or is it something that once you've cracked it, we can access pretty quickly because it's diagnostic?
The drug discovery is a big area, and obviously there are, like, I would say nowadays they start with millions of molecules and then hopefully one makes it to the end of the study, and there is a lot of money invested by companies and so on. Whereas from the academic point of view, for instance, I have one of the students in my lab that she's already focusing on a specific compound that is showing some hopefully protective effects against the irreversible damage following a heart attack and the exposure to that drug that I mentioned to you before. So we are trying to focus on trying to better understand, yes, we see some positive effects in a test tube. Can we translate it as quick as possible for the patient? And what are the different steps that are required to do that?
Yeah, it's extraordinary, isn't it, really? I mean, how much work is going on and then how much actually gets to the end of the day is, for both of you, I don't want this to sound like a Dorothy, but for both of you, I mean, I always despair at the amount of time you have to waste trying to apply for money to do all this work. How important has been the money that the donors who are watching this today to actually getting this work underway compared to what you would have had to gone through if you didn't have the money coming from those donors?
I'm happy to start with, or unless Avedis, you want to go first. But
That's okay. You go.
No, go ahead, Carmine.
Well, from my point of view, biomedical research is very expensive, and we all know that. And without the support of Heart Research Australia, we weren't able to, first of all, support some of the students, including Chris, one of our PhD students. He flew all the way from the UK to do his PhD here in Sydney, and he's a cardiac surgeon training himself. And before joining our lab, he's never seen a pipette in his life. And then thanks to the support of Heart Research Australia, he's finishing up his studies, and together with him, we showed the positive effects in the white mice that you were mentioning before. But at the same time, for instance, another big piece of research allowed us to establish research that we started overseas. For instance, in 2016, I visited a laboratory at Harvard Medical School, and I was able to use one of the microscopes that was very specific to understand on how these mini hearts are contracted. And there was no availability of this equipment here. And thanks to Heart Research Australia, we were able to purchase that equipment and many more that are basically supporting our research here, and to establish new research in Sydney that is basically bringing us to the forefront of the cardiovascular bioengineering research globally.
Well, Jenny, you know, it's extraordinary, isn't it, really? Today we've looked at how we're actually going to make the decision about whether we prophylactically put a stent in an artery to stop having a heart attack and therefore heart failure. And then we're now at the same time looking at, if we do have that heart attack and we're starting to get those cells that are no longer functioning properly, how can we make them immune to that effect so that the effects are not as severe? We're attacking all angles at once here. All the white mice of the world say thank you very much to both of you for all the work you've already done, and all of the humans of the world, I think, say thank you so much for the work that you're going to give our, particularly maybe not me, but certainly my children and grandchildren, being able to benefit from this extraordinary knowledge. And knowledge is everything. And I think you mentioned, Carmine, about repeatability. Science is about hypothesis, proof, and repeatability. And all this work you're doing is being repeated around the world, and that adds to its validity so much. We're so lucky to be able to be part of that by way of putting money towards it. And thank you very much for bringing it so clearly to everyone watching today so we can really understand what you're doing. I think your jobs must be some of the most interesting jobs in the world, and it's fantastic and a privilege to talk to you both. So, Jenny, have we got questions coming in from people that we could go to?
Yeah, we have got a few. But yeah, no, absolutely. To Chris's point, the work you guys are doing is incredibly mind blowing. And you know, as Chris said, it may not be us, but it could be our children or our grandchildren. And I think that the ramifications for this work, you know, for a family kind of point of view, for Heart Research Australia, our main core focus is to keep families together for longer. And you know, Chris's point himself. Has been able to spend time with his grandchildren and see his grandchildren grow. You know, this is extra bonus time that he may not have had, and you cannot put a price on that. And the amount of stress and pain that families go through when their family member is sick, or if you know anything happens to them, it's to have this work happen to potentially, you know, save people from that pain is incredible, and we're so proud to work with you and help fund that. So the first question we've got is. I think more for Avedis, we've had you have answered it, but I'll put it out there just in case anybody else didn't see it, or for the recording for other people. But is there any way to identify those cases in which a stent will do more harm than good? And you can read out your
answer. I did reply to that, but I'll just say sort of to the group that yes, that's what the research to date has given. Well-defined thresholds on these pressure wire studies. They give ratios basically of the blood blood flowing through the narrowing, and a ratio of using FFR, which is one modality. The ratio is less than 0.8 to benefit from a stent, and more than 0.8 to cause harm. So that's that threshold in which benefit exceeds risk. and the other modality is 0.9. That's the IFR modality. It's 0.9. But what we're seeing is that things are a little bit more complex than that. So you can't. It's a very what we call dichotomous cutoff, and not every human heart listens to the ratios, and that's why we need to refine the process a bit further to see which patients do these ratios apply to. So yeah, that's more or less the crux of it. Yeah.
And I think you were saying in some of our earlier meetings that so far with the research that you've been doing, you found that I think it was a 30% discrepancy between the two. Is that correct?
Yeah, that's right. It's that, which is a little bit higher than what has been published, but we're getting real world data. We're not, which is a bit different from the the very I guess clean data that you can get in some randomized trials sometimes. So this is real world, real patients, and so yeah, we're finding quite a substantial discrepancy, and really just trying to find what are the variables that have contributed to that discrepancy.
Yeah. And with the real world patients, are these sort of de-identified? Are you able to tell whether they're female patients or male patients, and is there a difference between the two?
Yeah, well, I actually do will do the procedures on them. My data is all de-identified, so but I will have those sort of demographic details. So everything is confidential. Everything is stored in a way that no patient's details will get sort of breached. However, I do store demographic details that I analyze. I got to say that I was just having a look at my updated data yesterday, and 75% of the patients I've done are male, actually, and that's just sort of luck of the draw. It's an all-comers study, but as it turns out, it's happening a whole lot more in the male community. So
that's more of a comment on our lifestyle, I think, than your research.
Probably, yeah.
It'd just be really interesting to see if there is a difference in the female results versus the male results. And to that point, Carmine, is there, when you've been looking at the molecular structure of a heart attack, have you been able to differentiate for if it's a female patient or a male patient?
Oh, thanks. Yeah, we can identify, obviously everything is anonymized as well. So we know the origin of the cells that we use. So we can understand better what are the effects on the male population versus the female population. I haven't mentioned to you guys, but we are also looking at specific conditions in women leading to heart failure following pregnancy as well. For instance, we do know that preeclampsia, which is a condition that occurs in some of the women during pregnancy, some of them actually develop heart failure as a consequence of the disease. And we are that
as part of peripartum cardiomyopathy, or is that separate?
It's separate, but what we're doing at the moment, together with other other clinicians at St. George's Hospital, well, we are able to collect bloods from the patients that that developed preeclampsia, and trying to understand by creating these personalized mini hearts how the disease the disease itself, preeclampsia, may lead to the development of the establishment of heart failure in a petri dish. Trying to understand the way the mechanisms that are leading to the disease, at the same time trying to understand better ways to potentially treat it or prevent it.
It'll be so interesting to just see the differences, and I know it's quite readily publicized and spoken about the, that there has been a real history of research being done, based on male patients, and that's why the outcomes for women aren't actually as strong as they are for men, because the research has been done based on men, and women's bodies are completely different, and their heart attacks are quite different as well. So it's really interesting and great that you guys are accommodating both sides and coming out with some good outcomes. So thank you for sharing with us. That's all hang on, I think we might have another question. Some of the researchers have questioned the efficacy of statins. What is the view of the panelists?
Maybe I'll comment. if that's okay, Carmine.
Yeah, of course.
I'm more than happy for you
It's all
to
yours.
add. But so yeah, look, I think that's it's an interesting question. Yeah, look, I think there's been a bit of bad publicity about statins, relating to the sort of small incidents that of muscle aches and that people can get, and very rarely what was referred to as myopathies, where you can get actual weakening of the muscles. But far and away, the cardiac research has demonstrated that it's that statins have substantial prognostic benefits, and there's even some studies that show some plaque regression relating to the use of statins. So meaning that the narrowings of the arteries are, we think of them as very well established, and that they don't regress, but in fact there have been some studies that show there has been some regression of plaque with the use of statins. So I would say that if you're and I should also mention that that there are research, papers, the ones that I'm aware of, showing that the lower the cholesterol, even if you have a good cholesterol, if you can push it even lower, that's even better for you. So in my experience and my knowledge suggests that statins are very good therapy, and you should probably take them if you've been prescribed them, unless you're having a rare side effect, in which case consult your cardiologist.
Can I speak as a patient about that heart attack? My cholesterol before that used to be usually around about 5.5, I suppose.
Yeah.
And I don't want to sound like you've all heard of the boy and the banana anecdote about during the Second World War, no bananas were available in England due to Ecuador not being able to get the bananas to England. So straight after the war, there was this little 6-year-old boy sitting on a train who'd never had a banana in his life. So he was on his way back home from boarding school, and he opened up his lunchbox, and both of them had a banana in it. So they looked at each other and said, "What's that?" And he said, "I think it's called a banana." He said, "Well, look, you eat yours and I'll watch and see how you go. And if it's any good, I'll have." Just as the little boy ate his banana, they went into the tunnel. And so he immediately yelled out, "Don't eat the banana." Now that's the sort of that can apply to these things. But from my point of view, I was put on statins as soon as I had my heart attack, as everybody was. And since then, although I also lost weight and I changed some lifestyle changes as well and all that sort of thing, nonetheless, my 3.5 since then. And generally it's between 3 and 3.5. Now, I don't know that I would have been able to achieve that. I don't know. It could be like the boy and the banana, but I don't know whether I could have achieved that without, the use of the statins. And other than that, I've had no other side effects that I'm aware of. And this is now, I had my heart attack 18 years ago. Yeah. So and I've had no other effects that I'm aware of since then. So speaking anecdotally, I'm who's on statins, that the cure is definitely not worse than the disease. And if your doctor tells you to take statins, my advice based on my experience is do what he tells you or she tells you, because they'll know best.
Yeah, absolutely.
Just to add to that, yeah, there's evidence that your cholesterol of 5.5 wasn't too high. I mean, it's above what it should be, but what we know is that for you, that's resulted in a deposit of cholesterol within the arteries of your heart. And so for you, that cholesterol level is too high. So it needs to be pushed down. The other thing is there's what we refer to as pleiotropic effects relating to statins, so that it's not just a purely cholesterol lowering effect. There's also anti-inflammatory effects, which are protective for the heart as well, and a whole host of mechanisms by which they work, that it's not just the cholesterol lowering thing that protects your heart, basically. So they are great medications when applied correctly. So yeah.
Great. Well, that's it, I think, for the questions. And thank you so much, Carmine, Avedis, and Chris, for your incredible thoughts and donating your time today to help us and share your work with us. So on behalf of all the panel of the people attending, thank you. So it was great. It was really, really great. And it's great for us to tell all our donors what awesome work that they're funding. So thank you.
Excellent. Thanks so much.
Right. Thanks so much, everyone. Bye.
Thanks, everyone.
Yeah.
Bye.
Bye.